2 with this red thing here. Red, yep. And then I'm going to recreate a slider, and I'm going to make the same rectangular box like so. And I'm going to pin them together. That's to recreate the crank and slider mechanism here. Okay, I'm just going to group the two of them together. Now, what happens is, as this goes further away over here, okay, so when it goes further away, what we can see is that this crank, this red line can no longer hit the circle. Okay, so in order for that to still work, what's going to happen is this blue part, the radius of the circle is going to have to move position. Okay, and what it's going to have to do is it's going to have to move downwards like this in order for this red line, I need a new red line, in order for this red line to be able to touch it. So as this rotates in a circle, so this is going to keep rotating around in a circle. So when this rotates around, when this position here goes all the way over here, like this, this means that your slider is going to end up at the front. And your connecting rod, which is here, is going to go all the way down to there. Okay, so that's how they stay connected. This keeps moving around, and the connecting rod follows it accordingly. Essentially, something like this in this video here. Okay, you'll see the crank moving around in a circle, and then it keeps moving across. See, it keeps moving all the way up and across, up and across. Something very similar to that is what's going on with this question here. It's moving left and right as this goes around in a circle. Okay, so what things we need to know in regards to this question is that the connecting rod always stays the same length. So the connecting rod has to stay the same length, which is the blue mechanism here, and the red mechanism, which is the crankshaft, which is the radius of the circle, so to speak. It's also the radius of the circle. The two of these stay the same length all the time. Okay, so that's grand. Now, what varies, however, is the length of this pink part here. This pink part will vary in length. So as an example, if the crank's going directly upwards, so I'm just going to grab this crank, and if I put that directly upwards, and then I move this connecting rod here, you can see that the pink line has changed length. Okay, so that's very important to note that the pink line is the only line that changes its length, while the blue and the red line, which is connecting rod and the crank, have to stay the same. Okay, and it's explained in this position, starting position, and C is the center of the slider, I believe. And then we can see that the this rotates around in a circle. And as I said, there's your radius of your crank, and there's your connecting rod in blue. And then as it completes a circle, you can see that once again that your connecting rod staying the same length, and you can see that your radius is the same. But what is changing all the time is the pink length. The pink length is the length CO. CO is different at different times. Okay, depending on what part of the circular motion you're in. Now, even if you didn't understand all of that, you could still do question A. The diagram below shows a particular position of the mechanism DCO at 15 degrees. Find COD. Now, which one's COD? C to O to D. So we're finding angle X here. And we know 15 is opposite 10 and X is opposite 30. This is a clear indication of using the sine rule. It's not a right angle triangle, so you're not going to be using SOHCAHTOA or Pythagoras' theorem. So sine rule is 30 over sine X equals 10 over sine 15. We're going to move sine X from division on the left to multiplication on the right, and that will be right beside the 10. we're going to put the sine 15 beside the 30. So we get 30 sine 15. Sine 15. Okay, now see that 10, it's multiplication on the left, which means I can turn it into division on the right. So put the 10 underneath. Okay, now we're going to sine inverse this number, whatever it is, soon enough. You could do it directly. You could go shift sine inverse 30 sine 15 all over 10, and you get 50.93 or 51 degrees. You should also write down that you did in fact sine inverse the whole thing, just in case you happen to go wrong. You do want those at 10 marks. So 51 degrees, happy days, done. Next question. As D moves in a circle around O, the angle A in the diagram below increases. Okay, so let's have a look. As said, the angle we're looking for is COD. Okay, so this here is 51 degrees. Now, if D moves all the way over here, we can now see that this angle is bigger than 51 degrees. And if D moves down here, if D continued to move around the circle and get lower, so this point D, we can see that the angle COD even gets bigger, because it's going to be COD, and it's going to be this huge angle here, which is above 180 degrees. Okay, so that makes sense. As D moves around a circle and O, the angle alpha in the diagram increases. The distance CX can be considered to be a function of alpha and written as f of A. Write down the period and range of f. Okay, period and range. A circle, because it is circular motion, it repeats itself every 360 degrees. Okay, so you could write down an answer of 360 degrees or 2 pi, because every single time the angle rotates a full 360 degrees, it ends up back where it starts. So this point D here, as you said, we're tracking D here, D's here, and it moves around, comes to this position, keeps moving around, comes to this position, keeps moving around, and eventually it's going to end up back where it starts, 360 degrees later. Okay, and that's the first thing. Now, the next thing is write down the range of f. Okay, so what is f again? Talking particularly about the distance of cx. Now, where is cx again? Sorry, I just have to look at this again. The distance cx can be considered a function of a. Angle a, distance cx. Oh yeah, sorry, my fault. Cx is in the next diagram here. So we can see that C, which is the center of your oscillator, all the way to X, this red line here, okay, is the distance we're looking at here, okay? So, as an example, if we're going to look for the minimum and maximum distance it's away from it. So see this blue part here, this is the crankshaft, okay? Now, the connecting rod, it's the connecting rod. Now, if D rotated all the way around and came back to exactly where X is, so D is where X is. What would happen then, however, is that C would get pushed backwards. Okay, C would get pushed backwards and it'll be back here. And this would be a distance of 30. So 30 seems to be the largest distance it will be away. Now this brings you to the next part. What is the closest distance it can get to? Well, the closest distance it can get to, now please remember X to O is a distance of 10. Imagine D was over the far side of the diagram. So D is here. This would set the crankshaft, the connecting rod which is the distance of 30, it will put it on the far side of the diagram. You must make sure it's still the same length, it looks a bit longer. Okay, there it is there. Okay, then if we can just rotate it up. Okay, and in this case, C would be a lot closer because C is connected to D. So C would be all the way up here. Okay, because C is moving back and forth. It's a slider at the end of the day. Now, remember that the full distance of the rod is 30. The whole blue line is 30. Okay, but the width of the circle is 20 because it's 2 radius, which is 20. So 30 take away 20 is 10. So 10 would be the lowest distance it's away. So it's 10 to 30. Okay. Now, write down okay. So we have our answers here. We have 360 degrees or 2 pi, and we have 10 to 30. Okie dokie. Okay. Now let's go back to this diagram here. Okay, I'm just going to rub everything out for a second. Now we already know. So 0 degrees. Now where exactly is 0 degrees? We're just going to figure out where does this diagram actually start from. Okay, so we're going to rub out all this. And we're going to start off with A. Now, 0 degrees for me, remember that was 51 degrees earlier in part A. 0 degrees would be straight across the point X. So when D is at the X value, that would be the connecting shaft here. This distance here would be here to here, which is 30. And we have that verified. That's 0 and 30 confirmed. Now, 360 degrees, which is the next part, is when D goes all the way around the full circle, like so. And it will also have to be 30 centimeters. Okay, so both of them are 30. The next thing to figure out is what would be 90. 90 is when D is placed up here. So that will be an example of D is up here, and that's 10. The connecting rod C to D is 30, so that's C, D. Okay. Un momento. And this would be C to O, because O to D would be a 90-degree triangle. I'm just going to figure out what length this is. I'll call it L. So 30 degrees equals whatever 10 degrees plus, sorry, 10 squared plus L squared. 900 equals 100 plus L squared. 800 equals L squared. And L squared, L has to be the square root of 800. Which is 20 root 2, otherwise known as 28.284. Now, the deal is that we're not looking for C to O, we're actually looking for C to X. So C to O would be, X to O is 10, but we just take away 10, and that means that C to X would be 18.28, because 18.28 plus 10 is 28.28. So that'd be 18.28. Okay, and this position D will also be, it's also the same answer when it's at 270 degrees. And 270 degrees is from here to here, 3/4 of the circle, because it's actually the same triangle except it's upside down. Okay, so it's the same triangle except it's upside down. Okay, so that'll also be 18.28. Now that leads me to 180 degrees. Is the last thing I need to figure out. Okay, and I'm on 180 degrees now. Now, if D is here, and that's 0 degrees, 180 degrees will lead you all the way across half the circle, which is over here. Now, this causes C obviously to get dragged inwards. C is going to get dragged inwards. I think we've already discussed this position earlier, that the crankshaft, the blue position here, has to attach to D, always. So always has to attach to D, and that'll be here. And we know that that's 30. We did this already. It's 30, and that'll be a 10 and a 10, which means that the distance C to X will also have to be a 10 because C gets pulled inwards, and that'll be 30. Oh, sorry, it'll be a distance of 10. And there we go. There is our diagram. Okay, now we're going to have to sketch this diagram using the following. We're going to have to grab this here. We're going to have to sketch it underneath. Lucky for us, this is the easy part of the question. Now, this is I found this question particularly tough, so I'd imagine that you guys at home would probably find this question pretty tough as well. So I'm just going to draw a quick diagram. We're going to go from 0 all the way up to 30, because 0 is your bottom amount and 30 is your largest amount, or sorry, 10 to 30 even. Okay, so just draw and use black. Okay, we go from 10 to 30, so I don't know, each one worth 5, 10, 15, 20, 25, 30. That's up in 5s. I could probably make it larger to make it easier to draw. So maybe each 2 is worth 5, 10, 15, 20, that's 25, 30. To make it a bit larger. Okay, I have to go from 0 to 360 up in 90, so I'm just going to go 0, 90, 180, 360, oh sorry, 180, 270, and 360. We're just going to draw this 0 and 30, this red dot here. Okay, and then we get 90 and 18, so that's 17.5, about 18.8 is there. 180 and 10 is here. 270 and 18.28, so 18.28 go here. And 360 and 30 is around there. And here we have this function. It should look at that. I won't get full marks for that. It's meant to be a bit more of a wave, like an S. Then it's meant to come down. Sorry, let me draw this off here at the moment. It'll be a bit more like an S shape. Yeah, it's a bit better. Something like that. Okay. Now, referring to diagrams 1, 2, and 3 at the start of the question, which of the 3 positions of the mechanism with a 1 degree in change in alpha caused the greatest change in position of C? Explain your answer. Oof, that is a very tough question. Referring to is the rate of change, and you'd be referring to the steepness of a graph. Now, the graph is at its steepest. When is the graph at its steepest? The graph is at its steepest. Let's reread the question again. Diagrams 1, 2, and 3. Okay. Diagram 1. In diagram 1, the angle is 0 degrees. In diagram 2, it's somewhere in between, like it's somewhere in between 0 and 90, so it could be around the 60 degree mark, somewhere in that position, or 51 degrees like it was earlier. Okay, we don't know what angle that is. I'm just going to give it a random value of 60, okay? And the last value is from somewhere between 180 and 270. So for argument's sake, I'm going to call that 220 degrees. So you have 0, 60, and 220. Okay. Now, if I go to my diagram, here's 0. 60 is around here. And 220 is around here. Now, we can see that, you can see by the slope that it's at its most steep at 0. It's just come up and it's starting to drop. And then it smooths out again. So you're dropping at your fastest here. Okay, so you're dropping at your fastest just as you get over the hump. So you're dropping. Okay, guys, I just sort of drew myself a new graph because I found this one sort of hard to tell just because I didn't draw it right. Now, as we said earlier, there's a starting position of 0 degrees, which is diagram 1. Diagram 2, we said was somewhere in the 60-degree mark, and diagram 3 was in somewhere in the 220-degree mark, somewhere around there. Okay, so if I just split this up, that's 90, and this halfway between there and there is 270. Okay, so 220, diagram 3 would be somewhere in here on its way upwards. Okay, it's at steepest sort of in the middle. At the point of inflection, it seems to be at its steepest. Okay, so you're not at your steepest at the beginning of the hump. You're at your steepest at the point of inflection. Okay, so whichever value is closest to the point of inflection should be the general one. Okay, so point of inflection is sort of subjective here. Okay, and what we're thinking is that the 60-degree one is pretty steep here. Sorry, around 60 degrees, so it'll be around here. That's pretty steep. And the other one, which is 210, is only 30. So this one here, the turning point was 180 degrees, and this is like roughly 40 degrees away from the turning point. Well, this one here is like 60 degrees away from the turning point. So I'd say position 2. Position 2, as is closer to the point of inflection. It's a steeper slope, is what my answer would be for this question. Position 2, as it's on a steeper point in the graph. Cool. C. The diagram shows another crank and slider set with different dimensions. 36, 31 from A to X, excuse me, and BAO being 10 degrees. Find R, the length of the crank, give your answer in centimeters, correct nearest degree. So this is a different type of question. Okay, so this is a very different type of question. Now, what I'm thinking is that this position, I'm thinking of a big cosine rule here. Yeah, that's exactly what we're going to go for. We're going to go for a cosine rule. So imagine this is R. So this whole blue line here, or this whole red line here, is 31 plus R. And we're after R here. And we're going to use the cosine rule. And angle A is 10 degrees. And that means that small a would be R. So it's going to be R squared equals. Now we can't just use 31. We have to use 31 plus R. So it's going to be 31 plus R is B. C squared is going to be 36 squared. Minus 2 times 31 plus R times 36 cos 10. Okay, so we're going to get is R squared equals, now it's going to be 31 plus R multiplied by another 31 plus R. Okay, so what's 31 times 31? 31 times 31. So 31 squared, 961. So 961. 36 times 36 is 1296. Now here's the tricky part. We're going to do 2 times 31 times 36 cos 10. Oh, that's going to be awkward. So 2 times 31 times 36 cos 10. That's going to be 2198.1. 2198.1, and that's just this random number here. Okay, so 2 times 31 times 36. The next thing we have to do is 2 times r times 36 times cos 10. Sorry, 2 times r, 2r 36 cos 10, and figure out what the next part is. Okay, so it's going to be 2 times 36 cos 10. This is a fantastic question. 70.91 or 70.906 even. Now, what we're going to have to do next is we're going to have to bring it all over one side and figure out what's going on. Now, I also see that 31 plus r squared. I haven't quite finished that yet because it's going to be r squared equals 961. It's going to be 31 times r, which is 31r, and then another 31r. 31r plus 31r is 62r. And then there's also going to be an r squared because it's r times r. Then the r squares are going to cancel. And then we're going to have our 296. Actually, I'll combine the two of them together. Our 296 take away our 298.1. And that is going to be minus 102.902.1. And we still have our 70 point, I'm going to call it 70.91r. Just going to round it off at this stage. Now, the r squared is cancelled, which means, thank God, I don't have to do a gigantic minus b formula, which I wasn't looking forward to. And now what we're going to do is add the 62r to the 70.91r. I think we're going to get 132.91r. Now, how does this work? Oh, I combined the two of these, so the 1296 doesn't exist. Now, un momento. Okay, so on the previous step, we multiplied this out, and we also got we multiplied all of this here. That's all of that there, and then we did 1296 minus 281.298. Yeah, that's where we got to minus 902.1. And then, oh, the minus 70.9 is actually a minus performed there. See the minus? That should have been a minus. Okay. And then, so that's a minus at the back here. That makes a lot of sense. Now, so that actually isn't 132.91r. That was completely wrong. It's 62 take away 70.91. So you'd be looking at the marking scheme and realizing you're not getting to the same answer. So that's why we knew something was up there before we committed any further. So it happens as the test goes on. So what was that? Minus 8.91. So minus 0.91r. Okay. And then you're going to get 961 take away 902.1. And you're going to get 58.9. That's going to be 58.9 on this side. And that equals 0. Move over to one side. 8.91r equals 58.9. Divide 58.9 by 8.91. by 8.91. And we get a result of 6.61, and round off to the nearest centimeter, it's 7 centimeters, which is what they asked for, correct, the nearest centimeter. All right, guys, that was a very difficult question, but look, best of luck with it anyway.